Welcome to all of you, our members and friends of the Royal Society of Chemistry Belgium section. I'm very pleased to welcome you to this evening's meeting, which is being sent to you from Louvain-la-Neuve by Fabio and with Tim in Brussels, and from London, where I am, and our speaker. But we're on opposite sides of the Thames, I think.
Yes, south. Yeah.
We are very pleased this evening to welcome Philip Ball, who's probably well known to those of you who are members of the Society as a regular contributor to the Royal Society of Chemistry's monthly review. He was before that and still is writing for the well-known, very popular scientific magazine Nature. I think you were correspondent there for some 20 years or so. And you've been writing for the popular press for a long time. Your major reason for giving this talk and for wanting to promote the work you've been doing together with two colleagues in China is to promote a book entitled The Beauty of Chemistry. And that, I think, is what you're going to talk to us about. So there really isn't much point in me going on with a long story about this. You are a fellow of the Royal Society of Chemistry, on the editorial board of Chemistry World and Interdisciplinary Science Reviews, and a regular contributor to journals like The New Scientist, the New York Times, The Guardian, the Financial Times, and the New Statesman, and a contributing auditor to Press Prospect, and for whom you write a science blog. So let's just turn to your talk. You're going to try to convince us, if any of us need convincing, that chemistry is not just a thing of many wonders, but a thing of great beauty. So let me hand over to you and say, look forward to hearing for your talk, and please give us your thoughts on the beauty of chemistry. Thank you very much. Over to you.
Well, Dr. Ball, can you share your screen once again, please?
Yes, certainly. Let me see if I do that. So I think if I share, actually, I think if I share it like this, that's the way to do it. So hopefully you can see that.
Perfect.
Sorry?
Okay, and if you can still see me, because I can no longer see you, but I'm assuming you can somewhere on your screen. Here is the book. And I'll say, obviously, a little bit more about it as I talk, but it's a rather splendid object, I have to say, produced by MIT Press. So I'm going to talk a little bit about how that came about. I wanted to, first of all, of course, to thank all of you for inviting me to come along virtually, sadly virtually, and talk to you tonight. I have to say, for anyone who might be watching, who might be asked to give a presentation like this, the rewards are very conducive. Mine arrived this morning, and I thought it would be appropriate to christen it in the beginning of this talk. It reminded me actually that many years ago I once saw a plenary talk by the wonderful supramolecular polymer chemist Helmut Ringsdorf at Mainz, who began his talk by uncorking a bottle of wine from his brother's vineyard. And by the end of his talk, he just managed to time it to drain the last drops from the bottle, to the scandal, actually, of some of the older members of the audience. Now, I'm not going to try and do that tonight, because if I do, this talk will either finish prematurely or never finish at all. But let me at least toast this. That's wonderful. Now, this is my subject, and I know I'm probably preaching to the choir here, but here we go. But first of all, I want to say that there are probably two types of people in the world, or at least I sometimes wonder if there are. There are those for whom an image like this sends shivers down their spine, and those for whom it sets the pulse racing. And I suspect I know which category everyone here tonight is in. And there's no denying, though, that plenty of people have bad memories of school chemistry. But for me and for us, I suspect there's just an irresistible allure to this sort of thing. And what first drew me to chemistry all those years ago was the stuff itself, was the crystals, the coloured powders, the pungent smells, ammonia, sulfur dioxide, and of course the explosions. I suspect that my experiences were fairly typical for someone who learned chemistry long enough ago that it was still possible to imbue that learning with a sense of danger. That's to say, I was delighted to discover that you could make an explosive, a touch-sensitive explosive, nitrogen triiodide, with ingredients that I could acquire, let's say, from school. Ammonia and iodine is all you needed. So you mix them, you dry the product on filter paper, and then it detonates loudly when it's touched, producing a cloud of purple iodine vapor. Lovely stuff. And I remember also in one lesson being allowed to stick a finger into a bowl of mercury. And I think this is an experience that actually every child should have at some point. I'd still remember marveling at that unearthly sensation, that glistening fluid that just seemed impossibly dense and yet wouldn't wet the skin. None of this, I am sad to say, matches the kind of experimentation that Oliver Sacks was able to do as a boy in the lab that he set up in his home, in an old laundry room. Now, Oliver's father was a pharmacist, and so getting the ingredients for him wasn't so hard. And he made chemical gardens from water glass, like this one here, which is an illustration from our book. And he tried to extract metals from their ore. He made ammonium dichromate volcanoes, and I was delighted to discover that he made nitrogen triiodide too. He said that the room that he did all this in led out onto the garden, and so this is what he says in his fabulous book, Uncle Tungsten. He said, if I concocted something that caught fire or boiled over or emitted noxious fumes, I could rush outside with it and fling it on the lawn. The lawn soon developed charred and discoloured patches. But this, perhaps, my parents felt was a small price to pay for my safety. Theirs own too, perhaps. In those days, it was possible for even a young person like Oliver in those days to go to a chemical supplier. He went to one in Finchley and buy things like a lump of sodium that he and his friend Jonathan Miller, yes, that Jonathan Miller, threw into Highgate ponds to watch it explode. All this is described in Oliver's wonderful chemical memoir, Uncle Tungsten, which I think is the best testament ever written to the fact that there's no field of science that works more on the senses than chemistry. The Nobel laureate Robert Woodward put it like this. He said, "It is the sensuous elements which play so large a role in my attraction to chemistry. I love crystals, the beauty of their form." In fact, he named his daughter Crystal for that reason. Their formation, liquids, dormant, distilling, sloshing, swirling, the fumes, the odours, good and bad, the rainbow of colours, the gleaming vessels of every size, shape and purpose. Much as I might think about chemistry, it would not exist for me without these physical, visual, tangible, sensuous things. So that was Robert Woodward's view, and I've seen nothing that captures these aspects of chemistry better than the astonishing videos that are made by Yan Liang and Wenting Zhu, my collaborators for this book. They make them for their project, their web-based project called Envisioning Chemistry. And some years ago, I was at a conference in China, in Shanghai, and Yan got in touch with me, and he jumped on a train, the new bullet train, really, from Beijing to come to talk to me about the possibility of collaborating. And that was my first introduction to his work, and I was entranced by it. And so I told him that I'd be absolutely delighted if the opportunity arose. Several years down the line, here we are, and here's the result. This book, The Beauty of Chemistry, published this year, and it's filled with amazing images of chemical processes, from crystal growth to bubble formation, from precipitation to the colour changes of flowers. And I hope that we've been able to reach beyond the stinks and the bangs that appealed so much to geeks like me, and to show that there's actually a much more profoundly aesthetic aspect to chemistry. that I think is unequaled among the sciences. Yen's work has been used by chemists all around the world, and you can see why. It featured in the opening ceremony to the International Year of the Periodic Table in Paris in 2009. In fact, if I remember rightly, Tim, I think that was the first time that I met you in person at that great event. Now, in all honesty, it was hard to capture in this book, in the still images. It was hard to capture the wondrousness of the videos that Yen and Wenting have made, which I think is a reflection of how beauty and chemistry is often dynamic, both at the everyday scale and at the microscopic scale, and indeed at the molecular scale. So I want to show you some of that dynamic work too. I want to show you a promotional video that Yen has sent me. So here things possibly get a little bit tricky, because I'm going to try and change my screen and show the video, and I'm hoping that you will be able to see this video as I play it. So if I bring this up now, now do let me know if that isn't visible on your screens. Does it all look good?
Yes.
Fantastic. Well, hopefully you'll hear the sound as well. I think it's really good to actually watch these things happening to see what Yen and Wenting have made. So here we go. Okay, I'll stop it there. Let's see if we can get back. Hopefully this will just take me back to where we were. And okay, there we were. Well, I mean, you can see that, you know, I looking at those videos again, it sort of strikes me that there's almost kind of data there. You know, they're so wondrously sort of detailed and full of richness. And there are all kinds of things going on in there, in those dynamical processes that make me think, well, you know, what exactly is it? There are, you know, it's almost as though you're watching it. Well, you are watching an experiment happen. And this astonishing beauty that resides in chemical products and processes, I think too often passes unseen, or at least unacknowledged, as being chemical in nature. You know, we can marvel at the delicacy of a snowflake or the rich brightness of a flower and its heady fragrance, but we can at the same time fail to realize that chemistry is at work here every bit as much as it is in oil refineries and pharmaceutical plants and lab benches. Now, I make no apologies for using this slippery word beauty in the title of my talk and the book, but I do want to acknowledge that actually it's a complicated one. I had to wrestle with that when about 15 years ago, I wrote this book for the Royal Society of Chemistry, which tried to push back a little on the rather uncritical and unreflective way that the word beauty tends to get used in science. Now, the Royal Society of Chemistry they commissioned this book from me. They asked me to pick what I considered to be the 10 most beautiful experiments in chemistry. And let me just show you briefly, for the sake perhaps of provoking discussion perhaps disagreement that we might have later on. Let me just show you the experiments that I alighted on for this book. So I'll just briefly run through them here. The first was Jan van Helmont's willow tree experiment in the early 17th century, Henry Cavendish's synthesis of water, Louis Pasteur's discovery of molecular chirality by looking at crystals of tartrate, Marie and Pierre Curie's isolation of polonium and radium at the turn of the century, Ernest Rutherford's demonstration that alpha particles are helium nuclei, the famous Urey Miller prebiotic chemistry experiment in 1952, published in 1953, Neil Bartlett's synthesis of the first noble gas compound, Robert Woodward and Albert Eschenmoser's synthesis of vitamin B12, and Leo Paquette's synthesis of dodecahedrane, and then the investigation by the GSI team at Darmstadt of the chemistry of seborgium, which they did by looking at I think it was just 7 atoms of this synthetic element that has a half-life measured in seconds. So it was just an astonishing masterpiece of very fast and very precise chemistry. But it was clear to me in compiling this list that what might qualify an experiment as beautiful wasn't necessarily the same as what might make a molecule beautiful, and that those criteria are again different from the notion of beauty that physicists often invoke when they, as they often do, enthuse about beautiful equations or theories, and all tend to be very different from what beauty is deemed to mean when it's brought up in discussions of art and aesthetics. In fact, that word has largely been banished from from art history and art theory for some time, and not without good reason, because artists are and art theorists are, I think, rightly skeptical about the idea that the purpose of art is to just make beautiful things, to beautify, to be decorative, basically. So in other words, there's actually a lot of baggage attached to this notion of beauty. If you ask a chemist what qualifies as a beautiful molecule, then you're likely to get an answer like this. This, of course, is C60, or Buckminster fullerene, called the most beautiful molecule in Hugh Aldersey Williams' great book about its discovery. And it has this perfect polyhedral shape. In other words, chemists tend to be Platonists, I think. They locate beauty in symmetry. Well, that's their prerogative, but I don't think that makes much connection with ideas of beauty in aesthetic theory. For Plato, art was actually too messy to be truly beautiful. But for Immanuel Kant, beauty depends on a departure from the regular and the perfect, as he put it, or stiff regularity, such as approximates to mathematical regularity, has something in it repugnant to the taste. Even Francis Bacon, and that's the 17th century philosopher Francis Bacon, not the 20th century artist, although he had some interesting ideas about beauty, I'm sure. Even Francis Bacon agreed when he said, "There is no excellent beauty that hath not some strangeness in its proportion." But I would defend our use of beauty here for this very reason. For one thing, Yen and Wenting's imagery says to me that that beauty is indeed in the eye of the beholder, not in the sense that it's all just a matter of personal taste, but because beauty depends on how you look. What's wonderful in their videos and their photos is not necessarily intrinsic to the processes that are being shown, but to the skill, both the technical skill and I think the aesthetic skill that they have used in determining how we see it. I think it's immediately apparent that their imagery isn't something that you can just capture casually. Their images are composed and selected and captured with great virtuosity, just as they are in the best for the best photographers. And this is what I appreciate so much about their work, because in my view, they help to instruct us about how to look and how to see, which of course really does then connect to theories of art. Now, I mean, I've conducted many precipitation reactions myself, for example, but I've never seen them. Sorry, that was Kant, but I've never seen them looking quite like this before. And I think that perhaps it's here that art and science might find some common ground, because both are concerned, first of all, with revealing things that we might not immediately notice. They show us what is there, and so they demand a special kind of engagement with the world beyond the necessary superficiality of our everyday routines. They ask us to really attend to what we're seeing. And that, I think, is where science itself begins, with attending, with noticing. Please forgive the cliche of invoking Leonardo da Vinci in this context, but one really has to, I think, here, because noticing and attending is key to everything he did. When he looked at the flow of water, as he did very often, what he was trying to do was to discern the deep patterns and forms beneath the superficial play of light and surfaces. So his sketches of flow patterns here don't actually look much like what we see. They're his attempts to reach beyond that, to the underlying patterns that he was sure were there. And I can't help but be struck by, given the lovely meeting, I think, of East and West in our book, by how similar this is to the way in East Asian art we often see flow structures depicted that are trying to capture their deep, complex, almost organic forms, rather than the sort of instantaneous manifestations of that you might get in something more photographic. And isn't this really what so much of science is about too? Trying to look at the underlying regularities and patterns. And to that end, science creates new tools for seeking and probing beneath the surface, for stopping time and magnifying space to capture what the eye can't see. Even high-speed photography was invented in the late 19th century, or when high-speed photography was invented in the late 19th century, experts like Harold Edgerton at MIT used it straight away to show us patterns and wonders in nature that we'd never before been able to notice by freezing time. This particular image, in fact, serves as the frontispiece for the 1942 revised edition of Darcy Wentworth Thompson's classic book on growth and form, which explored how structure and order and pattern appear across scientific disciplines according to some universal principles. I'd like to think that our book shares something of the same spirit as Darcy Thompson's in its own modest way. We look, for example, at some of the amazing patterns that emerge during crystal growth and at some of the chemical reactions that are known to generate complex patterns. Just the kind of processes that Darcy Thompson discussed, although at that point without much real understanding of what was generating them. It always amuses me that On Growth and Form begins with this general statement, Darcy Thompson says, of the chemistry of his day and generation, Kant, again, declared that it was science, but not science with a capital S, for that criterion, for that the criterion of true science lay in its relation to mathematics. It rather seemed that for Thomson, the chemistry of his day still hadn't quite attained that standard of the mathematical. Now, we can argue about whether it's done so now, but also I think about whether mathematization should in any case be the ultimate criterion for what really qualifies as science. What our book, The Beauty of Chemistry, is trying to do is instead, I think, to return to the real roots of that enterprise by revealing the truth of what the 19th century chemist and astronomer John Herschel once said. To the natural philosopher, there is no natural object unimportant or trifling. A soap bubble, an apple, a pebble. He walks in the midst of wonders. And here are some bubbles photographed by Yen and Wenting, the kind of thing that we might see all the time in carbonated drinks and in champagne. Again, it's a totally familiar phenomenon, but one that when we attend closely becomes utterly beguiling and full of questions. Why, for example, do bubbles take these wiggling sinusoidal paths as they rise up? What determines the bubble size? How are the bubbles nucleated? And this is precisely why I say that science doesn't, as is sometimes said, doesn't de-enchant the world. On the contrary, it re-enchants. It requires a willingness to find strangeness and surprise in the mundane. Once you start asking questions, there's little chance that you're going to exhaust them, even in a phenomenon as, old and familiar as the formation of bubbles. And for example, we've since antiquity admired flowers, but there's still plenty of gaps in our understanding of them. For example, in our understanding of how their colours are formed, let alone what purpose they serve in guiding the plant along the discerning byways of evolution. Yen and Wenting have produced a lovely series of images like these of the colours and how they can be changed by chemically treating the petals of the flowers. And I talk in the book about what we understand about these colours and about the pigments that produce them. And I show that sometimes nature arranges the pigment molecules themselves in wonderful, almost structures that are presumably delicately tuned by evolution, although for what reasons we don't always know. In other words, chemists are still finding the unexpected in what appear to be the most familiar objects, bubbles, flowers, even water molecules. And the fact that all these studies, all these questions begin in experience, in what we can see and hear and feel and smell in our own concrete reality, and the way it invites our attention and our appreciation. And I'll unabashedly admit that my agenda here and the potential that I see in Yen Wenting's work is to rehabilitate the status of chemistry from its common perception as at best a staid and sleepy science, and at worst a dull, dirty, polluting business. The age of John Herschel is more or less the one that was described by Richard Holmes in his fabulous book, The Age of Wonder, when chemistry was the preeminent romantic science. It was seen as a bridge between the scientist and, for example, the poet. This was the era in which, as Richard recounts, Samuel Coleridge would go to the Royal Institution to hear Humphrey Davy speak in order, as Coleridge said, to replenish his stock of metaphors. And Davy would return the compliment by composing poetry, not terribly good poetry, it has to be said, but not doggerel either, in the romantic vein. thanks to the, and here is Davy, thanks to the flair and passion of people like Davy, chemistry captured the public imagination. Sometimes it's true in ways that Davy might himself not have appreciated so much, as shown here in the famous caricature by James Gilray of one of Davy's lectures at the RI on pneumatic chemistry. Chemistry seemed then to be the science most likely to reveal the deep mysteries of nature, just as Mary Shelley, whose father knew Davy and who might have seen Davy lecture when she was still a young girl at the RI, as Mary Shelley tells us in Frankenstein, where she has one of the characters tell us that chemistry is that branch of natural philosophy in which the greatest improvements have been and may be made. John Herschel himself was a dabbler in chemistry, but in fact more than that, because he was a pioneer in photographic imaging, and his discovery of a way to fix silver using sodium hyposulfite was what enabled William Fox Talbot and Louis Daguerre to develop the craft of photography. Herschel was also the inventor of the technique of the blueprint or cyanotype, which was used by Anne Atkins to make images of plants that are now regarded as both botanical studies and as images of real artistic quality, again dissolving the boundaries between the arts and the sciences. All of this gave 19th century chemistry a cultural cachet and allure that seems far removed from its image today. It was an allure bound up with notions of craft, of science as a form not just of understanding, but of making. It was in the 19th century that chemists began to understand the transformations that they and their forebears in alchemy had been making for many centuries, to understand them as rearrangements of atoms and the sculpting of molecules that have distinct shapes. And chemists, I think, arguably today display the greatest creativity within the sciences, the greatest urge to make. Now, they're truly engineers of atoms, figuring out how to arrange them into new unions with useful shapes and properties, or perhaps just with a kind of beauty of their own. Here, many chemists are, of course, inspired by nature, which the Nobel laureate Frances Arnold, now a science advisor in the Biden administration, describes in our book as she puts it, she says nature is a brilliant chemist and by far the best engineer of all time. And how about this as an example of that? This is the it's a motor. It's the bacterial flagella motor, just 26 millionths of a millimeter wide, which exists in many bacteria. It's embedded, as I'm sure many of you know, in the cell membrane and rotates hundreds of times a second, driving whip-like appendages called flagella in a sort of corkscrew motion that sends them swimming through fluids towards sources of food. And earlier this year, a team at Zhejiang University in China published this detailed atomic scale structure showing how the rotor of this tiny device is made of protein, how it spins in these sort of ring-like sleeves of protein. It's hard to believe, but nevertheless true, that the process of natural selection could generate something so exquisitely engineered. So no wonder then that Francis goes on to say this about nature: I am among the many inspired by the beauty and remarkable capabilities of living systems, the breathtaking range of chemical transformations they've invented, the complexity and myriad roles of the products. I am in awe of the exquisite specificity and efficiency with which nature assembles these products from simple, abundant and renewable starting materials. And of course, nature assembles atoms into molecules like proteins and DNA, and from these constructs cells and organisms. And in doing so, it achieves the astonishing and yet to be understood feat of making matter aware of itself. I mean, that sounds like a poetic metaphor, doesn't it? But it really isn't. It's a simple statement of fact at which we should never forget to be amazed. Nature's exquisite chemistry allows parts of the universe to become conscious. Now, we humans, of course, are far less adept at this molecular construction, but we're getting better all the time. Frances herself has shown one way of doing that by finding ways of producing a kind of directed evolution, an unnatural selection in the test tube, by means of which we can make molecules like nature's own that can perform tasks that are not found in nature. And if you want to read more about that, this is a great place to start. This nice article in Chemistry World by Katrina Kramer. Now, in his novel, The Wrench, Primo Levi, the Italian writer and chemist best known for his works The Periodic Table and If This Is a Man, he drew an explicit analogy between the profession of the construction engineer who makes bridges and the synthetic chemist who makes molecules. The novel's narrator is one of the latter, and he tries to describe to an engineer who he befriends why their jobs have so much in common. He says, my profession, the profession I studied in school and that has kept me alive so far, is the profession of the chemist. It's a bit like yours, only we rig and dismantle very tiny constructions. The things we handle are too small to be seen, even with the most powerful microscopes. So we've invented various intelligent gadgets to recognize them without seeing them. But we are still blind, even in the best circumstances, that is, with structures that are simple and stable. Blind, and we don't have those tweezers we often dream of at night, the way a thirsty man dreams of springs that would allow us to pick up a segment, hold it firm and straight, and paste it in the right direction on the segment that has already been assembled. If we had those tweezers, and someday it's possible we will, we would have managed to create some lovely things that so far only the Almighty has made. For example, to assemble perhaps not a frog or a dragonfly, but at least a microbe or the spore of a mold. Now, I didn't know of that quote by Levi when almost 3 decades ago, I'm scared to say, I wrote this for an article in Nature based on a conference that we arranged on complex molecular systems. Instead, my title came from the challenge posed at the meeting by George Whitesides, the Harvard chemist, who said, can we harness and control molecular complexity well enough to make a synthetic dragonfly? 27 years later, we're still not there yet, but we've come a long way. We have tools now that can act like Levi's tweezers, which can let us pick up individual atoms and place them where we want them, that can allow us to tie knots in molecules and even to assemble individual molecules by pushing and prodding the components into place, like this work done quite recently at IBM in Zurich. Instruments like this can now show us single molecules like these that are revealed in this way of looking at them as a framework of struts showing the chemical bonds that look astonishingly like the schematic diagrams of molecules that chemists have drawn for over a century. And chemists have become accomplished at harnessing the principles of chemistry to make complex molecular assemblies like this one that we show in our book. This is a pair of interlinked rings called a catenane. And it was for making things like this that another of our book's contributors, who contributed a small text, Fraser Stoddart, was awarded the 2016 Nobel Prize in Chemistry, alongside Jean-Pierre Sauvage, who makes knotted molecules, and Ben Feringa, who has figured out how to fashion molecular assemblies like simple molecular motors. So not like the incredibly complex flagella motor that we saw earlier, but nevertheless motors, chemical motors, single molecules that can induce motion on command. And I think Ben will admit that our artificial motors, they don't have that elegance of the natural ones yet, but we're learning. Now, I know that Fraser and Jean-Pierre and Ben all find motivation for their work in the aesthetic response it invokes. This is how Fraser expressed it in our book. He said, one of the really beautiful hallmarks of chemistry is its ability to keep reinventing itself over and over again. This endearing virtue places the chemist in the same arena as a painter, sculptor, or musical composer. And the unique challenge for the chemist is that molecular beauty is not something that we can see directly, not without these special microscopes and other instruments that reveal the molecular world. But what we might find there can amaze us. Fraser says, in many ways, small is more beautiful than we might expect at first glance. And I can't resist quoting too from the introduction that Ben has just provided to the Dutch edition of my second publication this year that celebrates the aesthetics of chemistry, an illustrated history of the elements. So as well as offering a bit of advertising, I think Ben's words here testify to the allure of beauty in exciting the imagination and sparking the interest of young people in chemistry. He says, wonder and mysterious beauty is what is still clear in my mind. When I first saw Joseph Wright's painting, The Alchemist in Search of the Philosopher's Stone, here it is, during my school years, the discovery of the element phosphorus, this is what's being depicted in this famous painting, I felt like the little boy in the corner of the canvas, fascinated by the glow of pure phosphorus. So to my mind, Yen and Wenting's images and videos are a bridge to this kind of beauty, showing us that if we can learn to look in the right way, it can conjure up wonders at everyday scales and in everyday settings too. And we hope that our book will inspire people to think about the chemical world in this new way as one of the wonders of nature, filled with artistry, inventiveness, dynamism, and yes, beauty. Thank you all very much.
Super. Like that. Okay. Right. Oops.
You're on mute, Bob. It's gone suspiciously quiet. I hope I don't have to do anything to to rescue that, do I? I don't know. I think Bob, you're on mute at the moment, Bob. Yeah. Are you unmuted there, Bob? Well, while Bob unmutes, maybe. Well, thank Philip very much for that incredible, entertaining and informative presentation. Are you okay? Are you there, that Bob? Nope, still not on. It's full of interesting items. I now know where blueprint comes from, which I had never quite understood before, I have to say. Indeed, cyanotypes were used to make blueprints, so that's exactly it. Yes. Yeah. Okay. Well, I mean, we should open up to the floor. Does anyone have a question? I'm sure you must be many questions. Anything from Bo? Oh.
Toledano Lanza, please.
Yeah.
Thank you. Yes, thank you, Philip, for the wonderful lecture. I'm working in the European Parliament, and I have a question and a comment. The question is related to the Parliament. The day before yesterday, and also to your comment on beauty and the concept of beauty. The day before yesterday, the Parliament almost unanimously, only two MEPs voted against, passed a resolution trying to eliminate asbestos from buildings because it's harmful. Now, my question would be relating this to the beauty of chemistry that you mentioned at the beginning of your lecture. Was asbestos beautiful at some point in the past? That would be the question, and the comment, which is might be also a suggestion. for everyone is about an American photographer called Walter Wick, I think from Florida, or he lives in Florida at least, that has very, very nice books. He's a photographer, he's not a chemist, but very nice books trying to show also the beauty of nature, standstill photography, so drops of water and that kind of thing. Walter Wick.
Right. Yeah, I haven't come across him. I'll definitely have to look that up. I mean, of course, Edgerton's work is always worth revisiting as well. It's amazing what he was able to do, you know, even way back then. Asbestos. Well, I'm not aware that asbestos was ever sort of used and appreciated for its aesthetic values, as opposed to its sort of what was seen as utilitarian values and its convenience. But your story very much reminds me of the story of cadmium. Cadmium was discovered in the 19th century, and it was found that it has these colorful compounds, in particular the sulfides, and was used as a pigment. In fact, several pigments: cadmium yellow, cadmium orange, cadmium red, and these were, the cadmium red in particular was one of the strongest reds, one of the strongest inorganic reds, and it was used, you know, a lot by people in the early 20th century. People like Matisse was particularly fond of it, and still today, some painters will say we don't have a red to match cadmium red. We have these modern sort of organic pigments, you know, which kind of mimic its color, but nothing that really performs as well as cadmium red itself. But there has been talk at the European Parliament and elsewhere about certainly regulating and potentially banning cadmium, because of course it is mildly toxic, and this has created a lot of alarm among some artists, whether they're going to lose one of their favorite colors for which they don't really have a suitable replacement. And it's inspired some chemists to look for possible inorganic replacements to cadmium, and no one has quite found one yet, but I think that search, you know, still goes on. I'm not aware at the moment of the current status with cadmium. I don't think it's been completely banned. It's still possible, I think, to get hold of original cadmium red, but certainly that's a material or an element, a chemical element, that has been appreciated for its beauty or its aesthetic properties in the past that, you know, now may fall foul of regulation.
Okay, thank you very much, Miguel. I have another question. I have a question from Nadine.
Yes, hello. I want to go back to what you said about beauty is in the eye of the beholder. Before I was in chemistry, I worked in architecture.
Sorry, that's it. That's
And
it. Go back. C'est bon? Okay.
I'll just see whether you're on.
can you hear me?
Yes, I can. Yes, I think.
Yeah, sorry.
Back now.
So for a while, I worked with an architect who was intrigued with this notion of beauty.
Back in when.
And what makes something beautiful for someone and not for someone else. And so for about 3 years, I think we collaborated on research on what determines beauty and trying to answer this question. And funny enough, every time we went to that question a little bit historically, we ended up in the same place, which is linking beauty with the divine. And so looking at those very nice pictures that you presented, I was wondering, where do you stand on the question of intelligent design?
In terms of the our aesthetic response to what we see in nature, I feel that there are very plausible evolutionary reasons why we can imagine that that's so. So I certainly don't see any reason to imagine that what we perceive as beautiful in nature has been put there somehow for our benefit, for our aesthetic pleasure. I think it's much more plausible that we have, of course, co-evolved with the rest of nature, and that there are aspects of nature that we have come to have an aesthetic appreciation for, because they have some value to us, some survival value to us. you know, our sensitivity, at least to color, is, I think it's fairly clear that that is related to the abilities, the color sensitivity of other primates for figuring out what it's good to eat, what isn't. But there's I wonder if I've got it here, actually. I probably don't have it to hand. There's a nice book by the art historian Martin Kemp called Structural Intuitions, which is his name for a notion that the response, the aesthetic response we have to patterns in nature, and you know, some of the ones, if you still see my screen at all, some of the ones we might see here, that you know, complex forms and patterns in nature,
including symmetry, by the way.
Yes, including symmetry. Those two are they have an evolutionary basis, that they are, you know, we find them pleasing perhaps in artistic creations because they often mirror what we see in nature, and there are evolutionary or adaptive reasons why we might have found them rewarding in nature. I mean, one of them, I think, is simply that our minds are intrinsic pattern seekers. You know, that is that is one of our superpowers as humans. We're very, very good at spotting patterns and regularities, again, for adaptive reasons, because, you know, if you're able to sort of spot something coming, you're a bit better prepared for it. And the argument goes that, for example, music plays with our pattern forming propensity in audio input. Music sort of plays with that in ways that sort of stimulate and play with our emotional responses that perhaps are there in order to motivate us to respond in useful ways to the, you know, the patterns that might we might hear in the natural world. So I think you know, there are at least plausible evolutionary arguments why we should have this response to nature. And in my way of thinking, that means, in a sense, we're putting beauty into nature. Nature is what it is, but our minds have evolved to have some aesthetic response to it because there is an adaptive value to that.
But
Go on
even,
now.
even when you think of things like selection, our perception of beauty also plays a role, for example, in selecting a potential mate, let's say. With regards to music, I think one of the rhythms we grow up with before we are born is the regular heartbeat, which I think is regularity sound that soothes us, and I think we carry this even later on in life, whether we remember it or not.
There is certainly this idea that perhaps, you know, some of the rhythmic sensitivity that we have is due to the heartbeat. I've never seen, I have to say, completely convincing. I mean, it'd be very hard to get convincing evidence of that. It's very hard to get convincing evidence of anything from the preferences of even newborn babies, because we can hear in the womb and they will be exposed to, you know, environmental sounds as well in the womb. So establishing whether or not that's the case is very hard, but I think it's that's a plausible possibility. Yeah.
I think I might try to get back in if I can. Can you hear me?
Yes.
Yes, this time. Okay. My apologies. I seem to have managed to unmute myself. Boo, you had a question?
Yes. When I was a boy, it didn't exist. But, well, you talked about colors. And, of course, chemistry is an important factor for creating colors. And it didn't exist when I was a boy. But for my children, I think one of the first experiences they have had with chemistry and colors is when they got toy car, and when you heated it up with your hands it changed colors. And also when they had white sheet of paper, and just by adding water with a brush to it, it turned into a painting. So it's a lot of different combinations of chemistry into that, I suppose. And have you any comments about that?
Well, I can certainly say I don't think because I can't see what's on my screen, I can't tell whether I can move my camera to show you. But up behind me here, there is a rack of pigments that I keep there that I bought from Cornelison's wonderful colour shop in London. So there's ultramarine, there's cadmium colours, actually there's chromium colours, chromium yellow, and so on. And I keep it there partly because I wrote a book about colour and how the development of chemistry affected the colors that artists had available and how that changed the use of color and ideas about color in art. So it's something that's very close to my heart. But I have to say that I also keep this rack of pigments there just because it is so glorious to look at, because I love these colors. The pigments themselves, you know, the pure chemical compounds before you mix them with an oil to make a paint, they have a kind of intensity of color, a luster that it's very hard to capture in the paint itself. That was actually what inspired the French artist Yves Klein to develop his famous International Klein Blue, which is basically synthetic ultramarine in a particular fixative resin. It was a resin made by Rhone Poulenc chemicals company that retains the kind of luster of the dry pigment itself, and that was really what he was after. And you know, I always find that was this was done in the 1950s and 1960s, and I always find that that's a lovely reminder that even in these modern times where chemistry seems able to produce, you know, endless colors for artists, there was still this close association of artists and painters with chemistry, and they still, you know, relied on it. Yves Klein collaborated with a Parisian chemical manufacturer and paint manufacturer called Edouard Adam to make this International Klein Blue, so he needed chemical help to do it. So yeah, I think it's wonderful that, you know, there is still this association of chemistry with the way color is used aesthetically in the arts.
But I was specifically referring to pigments that are changing color due to process like heating or adding
or acidity or pH, you mean,
or something.
Yeah, well, absolutely. This is the wonderful thing that, you know, as chemists in particular, chemists and material scientists, as they come up with these new possibilities for color, so thermochromic materials or iridescent materials that are nanostructured, you know, that have a sort of layered structure, so you get this sort of pearlescence and this change in color of different viewing angles. These are produced, you know, by chemists and material scientists for technologies. These pearlescent pigments were produced for the car industry. And then along come artists and say, oh, I like the look of that. I'm sure that we can do something interesting with that. You know, that they'll take them away from the original intended use and do something, subvert really the reason why they were invented. So, you know, artists are making use of LEDs, which, you know, again are reliant on chemistry. Making the first blue light emitting diodes were, you know, required the synthesis of very good epitaxial films of gallium nitride, and you know, they were done for the electronics industry, and now artists are using, you know, multicolored LEDs for all sorts of purposes. So I really appreciate the fact that, you know, there is still innovation in color coming from chemistry and chemists and material scientists, and artists are still very willing and eager to seize it and make use of it, and sometimes to subvert it.
And indeed, to follow up on that, chemistry is now enabling us to tell when a piece of art is genuine and when it isn't, by virtue of the kind of pigments that were being used. Because as new pigments were introduced, artists began to use them. So you can tell if a particular pigment is being used in a painting that claims to be a Rembrandt, it can't possibly be, because that pigment wasn't discovered for another 100 years.
Well, that actually is what I'm just saying. If I've got a copy to hand here, that is what inspired me to write my book about called Bright Earth, about chemistry and color, because it was going to a talk by the late Robin Clark of UCL, who worked with the National Gallery on analyzing pigments in old paintings. And Robin, gave this talk about some of the very specific work he'd done for precisely those reasons, for identifying the pigments and, sometimes figuring out if the work was genuine because of their age. And it made me realize I'd never thought about this before. I'd never thought about where these colors come from, and when were they available? When were they made available? And the more I looked into that subject, the more I realized that it was possible to actually tell the history of art through this medium of the chemistry of color, and not just the history of art, but as you say, the history of art forgery, and art dating, which is a fascinating subject in its own right. And you're absolutely right that there have been forgeries identified, that because the artist, the forger, has used modern colors, modern pigments as a stand-in for ones that weren't around when the painting was supposed to have been painted.
Do we have other questions? Julie? I'm just looking along the list. Fabio, can you see any more questions around?
Not yet. Not
yet. Well, then I can ask the question now that I asked in a vacuum. Sorry, my microphone somehow got switched off. I was just mentioning another book related to art and science, which was, of course, The Two Cultures of C.P. Snow in the 1960s. And one of the things that came out of that debate was that scientists seemed to be somehow or other able to communicate with artists, but artists didn't seem to be very good at understanding what scientists were about. Is that still true of chemistry and art?
Well, there's, I think it would be fair to say that there's quite an emerging sort of consensus, certainly amongst people who study those interactions and look at the history of science. There's a view today that C.P. Snow's argument about the two cultures was a very sort of reductive and somewhat simplistic one. I mean, you could, to put it a bit unfairly, I must admit, you could reduce it to him saying, isn't it time that that people in the humanities, literary scholars, learnt a bit of thermodynamics? And maybe that would be a good thing, but I don't think that that's necessarily the solution to creating a dialogue between them. And I think that actually these days there is quite a thriving dialogue between arts and sciences. I mean, I've mentioned already how artists are very eager to keep an eye on what developments are happening in science and technology to see if they can make use of them. They're using also fiber optic technologies, communication technologies, all kinds. So, and often when they do that, particularly if it's a very advanced technology, they will need technical help to produce their images. So people like, for example, Cornelia Parker do, I think, call on scientists and technologists for assistance in what they're trying to do. So I think there's a lot of dialogue between them. Just last week, I was at a science festival in Portugal where I met an artist who had been working in the thriving sci art program at CERN, which has been going for some years now. And CERN is very keen to bring scientists in, to bring artists in to the facility. Really, I think, to be honest, with the hope that the artist is going to stir things up and challenge people and do the unexpected, not just sit in their sort of office and make nice things that have something to do with the Higgs boson, but actually get out and sometimes challenge the scientists to think in new ways about their work. And what I've heard is that actually, some of the scientists at CERN really appreciate having someone there like this, because it can, when it works well, it really can stimulate the scientist to think in new ways about what they do, that the artist might see things in their work that the scientists themselves hadn't really noticed or appreciated or thought about deeply, but that would benefit them from doing so. So I think there are reasons to actually be much more positive these days than C.P. Snow was about the interactions between the arts and sciences, going in both directions. You know, as I say, artists really are genuinely interested to find out what the sciences are up to and to use the sciences as a source of inspiration. And there are at least some scientists who appreciate that and appreciate those interactions and find them stimulating.
Yeah, in many ways, I think this goes back to the old idea of the senior common room or the faculty club in universities, where in fact scientists and arts and people from all sorts of faculties meet and talk and exchange ideas. And I frequently found when I was in Glasgow, it's one of the things I lack being in the European system, where this sort of faculty atmosphere doesn't exist. I found it very, very stimulating in Glasgow to be in contact with theologians or historians or linguists, because they cannot come up with ways of thinking which can actually be translated into a scientific context, I think.
Oh, yeah, absolutely. That was absolutely the context that C.P. Snow was talking about.
Yeah.
And famously, in particular, his rivalry, perhaps, with F.R. Leavis, the
Yes.
literary scholar. And, you know, that sort of senior common room atmosphere was very prevalent. Of course, it was in 1959 that he gave the Two Cultures lecture. And that was absolutely the world of, you know, Oxbridge in particular then. So that's really where it was coming from. And it's great to hear that there's less of that today.
Do we have other questions?
Yes, Tim, please.
Yes, I have one more question.
Yeah, sure.
Sorry, Tim.
You mentioned that high-speed photography was already started in the late 19th century. Where do we stand today? Are we down to microseconds or nanoseconds, or what is possible technically to do today to photograph reactions, etc.?
Well, it depends, I guess, on what you decide to allow as photography. But of course, if we're thinking of getting a kind of snapshot of very fast processes, then we're actually pretty much in the attosecond regime. You know, certainly the work that, in particular, that Ahmed Zewail, the Nobel laureate, did in femtochemistry really sort of paved the way. So and that's using lasers. So because we can make laser pulses that are so short that are, you know, femtoseconds long or shorter, it's possible to essentially use that as a kind of a strobe for looking at chemical processes. So Ahmed, you know, famously looked at the things like in real time, the making and the breaking of chemical bonds, watching atoms in effect, watching atoms, you know, come together and move apart. So he was doing that on the femtosecond time scale, which is a kind of, you know, the relevant time scale for that sort of process. But there are some processes involving, for example, electron rearrangements that happen even faster on the attosecond time scale. So that's 10 to the minus 18 seconds. And it's now possible to make laser pulses that are that short, and there are people who are doing that. So, you know, it's a kind, you could call it a kind of photography. It's really a kind of spectroscopy, of course, and it's allowing us to really see, you know, fundamental processes happening at the level of individual, not just individual atoms, but individual fundamental particles. So it's really astonishing, I think, you know, where that ultra speed has come today.
Thank you.
Okay. Any other questions?
Well,
Yes,
I've got possibly a last question, and the risk of opening a massive can of worms. I mean, it's good to see that humanities and sciences are interacting more. I'm just wondering if there's any more, whether in the current context of pandemics, etc., it would be good to see politicians and science interacting a little bit more in a positive and manner, perhaps.
Yeah, well, you know, I think the cynic in me wants to say that you know, both artists and scientists are interested in asking questions in an open-minded way, and that doesn't work so well in politics. And I think the part of the reason for that, I'm sure I'm not alone in thinking that there's just been this really dispiriting debasement in political discourse over the past 5 years, but it probably goes back further than that, in which any sort of admission that you don't already know the answers and that your answers are the right ones and are immune to any further challenge, you know, that anything to the contrary, you know, it just doesn't really sort of work in politics anymore. So that is dispiriting, because that seems to set up a fundamental disconnect between what science is about and what politics is about, not just in terms of asking questions versus, you know, asserting that you have all the answers, but I think more particularly, and this is really what we've seen in the pandemic, between science always being ready to acknowledge uncertainty and contingency, and politics finding both of those things to be increasingly unacceptable in today's political climate. You know, and we've seen that having, I think one has to say, fatal consequences during the pandemic, where, you know, in the early days when things were, of course, not well enough understood in terms of how the virus transmitted and how it manifested itself in the disease and so forth, that we often saw not just politicians actually, but also sometimes scientists working in the political arena voicing far too much certainty about things like this, premature certainty. And I can't help thinking there was a kind of infection coming from politics into science sometimes that led to this. That almost the scientists perhaps felt that they needed to, you know, give this sort of level of false certainty. So I think that that's a very worrying thing, and I think that's really the perhaps the, you know, dialogue that we need to sort of figure out how political policy, when it is reliant on scientific advice, how it can be sensibly made and conveyed while sort of acknowledging that it has to be contingent and uncertain. That's the challenge we face.
Thank you very much, Phil, and thanks to all of the people who asked questions. I'd just like to take this opportunity once again to say thank you very much for this very stimulating and interesting talk. I'm sure that many of us will be looking to the beauty of chemistry when we get it on our shelves. I'd just like to say a couple of words to thank not just Phil, but Tim and Fabio for the help with the preparation, and my apologies for the slight disconnect that we had at the beginning of the discussion section. Remind you that we still have one more event left in 2021, which will be again a virtual lecture by Jean-François Gouy on battery technology, and we look forward to seeing you all then. And in the meantime, have a very good evening. Thank you once again, and look forward to seeing you at the next of these lectures. Thank you again.